It's louder, yeah. So we wanted this condition for these simple inflation models. But a question was, don't we need also that V over M Planck to the fourth should be much less than 1 for the validity of gravity, right? And aren't these two in conflict with each other? So that was the question. And it is true that we need this condition. Indeed, we need this condition. And this condition is equivalent to the condition that H over M Planck should be much less than 1, right? And this is the same as saying that the radius of the de Sitter space should be much bigger than the Planck units, right? So that's that we need. Those are all conditions that we need. These are all equivalent, and they are conditions that we need for the validity of the effective field theory. So Einstein's theory of gravity is an effective field theory, and we need this condition for its validity. And naively, you might at first sight think these two are incompatible, but let's look at one example to see how we can make them both compatible. So let's consider the special case, let's say, of n equal to 2, for example. This is just some example. The other cases work similarly. So we have this as the potential. And so we want this condition. And in addition, with this potential, we want the condition that m squared over phi squared over m Planck to the fourth should be much less than 1, right? So we want these two conditions. Shouldn't have written here. Then from here we see that this is m over m Planck squared. We write it like this. Now, by this condition, this factor is much bigger than 1, right? So this is much bigger than 1. But the idea is that we will work in a regime where this m is much less than m Planck. And it is so much less than m Planck that it multiplied by this, which was bigger than 1. Okay. Now this is how much bigger is this? So this factor had to do with the slow roll factors, which are maybe 1% or a few per mil or something like that. And so this must be much smaller than that. So what that is saying is that if we are talking about a potential like this, so this is the phi squared, m squared phi squared potential. So we saw last time that when phi is in this region in the middle, we did not have slow roll, right? When phi is so this is phi. This, let's say it's m Planck here. So when phi is in some region here, we had slow roll. But when phi is very, very large, here we have no control. So here the theory breaks down. We cannot talk about phi in this region. But there is a whole region where we can talk about phi, okay? And we can have slow roll. We will later see in later lectures that even this regime is divided into two parts. One is the slow roll inflation regime we are talking about here, and there will be a slow roll eternal inflation regime that we'll talk about that later. Okay, so that was one of the questions. Then there was another question related to f of r gravity. So we so people sometimes discuss f of r gravity. So a theory whose Lagrangian is a function of the scalar curvature, or Ricci scalar. And we had said that this was equivalent to a theory of ordinary gravity plus some scalar field plus some suitable potential, where this potential depends on this function f. Now, a particular example was r plus r squared. And the question is, the question was, how can it be that here we really have the metric? We started with a theory that had only the metric, so we would naively say it has only gravity. But then it's equal to a theory that has one more degree of freedom, gravity plus a scalar. So how can this be? Is there a simple way to understand why we have more degrees of freedom? So a general point is that because we write the Lagrangian in terms of some field, it doesn't mean that the degrees of freedom are, the same in all possible theories we can write with those, all possible Lagrangians we can write in terms of those fields. So the fact that for Einstein gravity there are two massless photons does not guarantee that for this theory we'll have two massless photons. In fact, it's not true. So in general, the on-shell degrees of freedom, or the actual physical degrees of freedom from a Lagrangian, you have to work to find them, right? And so in this particular case, we know that the Einstein, the curvature has terms with two derivatives of the metric, so terms roughly like this, and then also terms with this kind of structure, okay? Now this is schematic, and if you wish, as a toy model, we could consider just a theory where h is a scalar, and we, let's say, define some variable r, which is this quantity, right? Now, if we had a Lagrangian that contains only r, then the integral of r, so the first term we can integrate by parts and doesn't contribute to anything, and we'll just have an action which contains d squared h. So h is the, let's say, degree of freedom, okay? Now, if we had a term that involves r squared, then when we take the square of this term, we'll get a new kinetic term, which is dh squared. So something with 4 derivatives, okay? Then we can rewrite this by adding a scalar. So by adding another field, let me call it phi, dh squared plus phi squared. So if we integrate out phi, we get back this term, okay? But now we see we have the scalar, and now we see we have a second degree of freedom, which is the scalar. So we could rewrite this as d phi dh plus well, something else. And so now from the r term we had the let's say graviton degrees of freedom, and here now we'll get the scalar degree of freedom. So this is roughly the mechanism by which this is essentially the mechanism by which we get an extra degree of freedom. Okay. Very good. So is that clear? Good. Okay. So those were two of the questions I wanted to answer for everyone. So now I'd like to continue part of the general discussion we had this was part of the general introduction to inflation. I wanted to mention basically what are the experimental constraints on these low roll parameters. We'll later understand in more detail where these constraints come from. But basically there are two constraints. The first constraint comes from the non-observation of gravity waves. So inflation predicts gravity waves, but we haven't seen them. And so that implies that epsilon is less than 3 times 10 to the minus 3, okay? And then there is the observation of the fact that the scalar fluctuations are not exactly scale invariant, but there is a small deviation from scale invariance. And that small deviation is sometimes called ns minus 1. So there is some, we'll see what these parameters are, but there is something that is being measured, which is the deviation from scale invariance, and that is equal to, let me remember the sign, we will later derive this formula, so this is, we will derive it when we discuss in detail the spectrum of fluctuations. But the point is that from observations, in particular from the Planck satellite, together with some other large-scale structure measurements, we have this clear deviation from. So when this is 0, the spectrum is scale invariant, but we have a clear deviation, right? So this 4 is here in the second digit, so we have an error of let's say 10% for the deviation from scale invariance, okay? And we have a kind of small deviation. Okay, so that kind of gives you an idea of what this low roll parameter should be, right? So this is just only a bound, but here this in particular, together with this bound here, implies that eta has some range, some finite range. So for example, well, you can work this out, but in particular, you can check that because epsilon is relatively small, so it's smaller than this value, there is a 3 over here, and you'll find that eta, for example, has to be negative, right? So the potential it cannot be a potential that curves up. So remember, eta was related to the second derivative of the potential, right? So it's telling us that the potential should have a negative second derivative. So it cannot be like this. So this type of potentials are ruled out. It has to be something that curves down, okay? Very good. I mean, we could have a power law potential with n less than 1, and then it would be okay. Very good. So the conclusions are that inflation is a very nice scenario for what happened before the Big Bang. It kind of explains both why the universe is smooth and why there are fluctuations. And it's not a unique theory, so it's not just a theory like the standard model that has a few parameters. So here it's a theory that has a whole function in the simplest case where we have one field. If we have many fields, there are many functions. And in principle, we could fit the data. I mean, here we see that we are fitting the data by modifying these parameters, right? We fix epsilon and eta, and basically all the measurements that have been done translate to fixing these parameters. Okay, so you could say, well, inflation is not predicted; it's just simply a fitting of the data. I think this is not a fair assessment because inflation is also predicting other things like the fact that the universe is flat at long distances and the statistics of the fluctuations and so on. So it does have definite predictions. Okay, so we now will discuss in detail the computation of the fluctuations. Let me just give one philosophical point of why we can compute them. So we'll compute some quantum effects. There are quantum effects that involve gravity because we have gravity and the scalar field both coupled together. And we can do these quantum gravity computations because we are treating this theory as an effective field theory. And we are going to be in a regime where the effective field theory is valid. And as I mentioned a moment ago, the validity of this effective field theory depends on the fact that h over n Planck squared is much less than 1, right? And remember that I mentioned this is the parameter that controls the amplitude of the fluctuations, and that amplitude is 10 to the minus 10 if we put the 1 over epsilon, and if we remove the 1 over epsilon, this is even smaller than that. So we're in a very well weakly coupled regime, and that's the regime in which we will do the calculations. Okay, so it's a well-defined theory, and we can do the calculations. We don't need anything fancy like a full theory of quantum gravity and so on. It's enough to consider it this effective field theory. Okay, now I'd like to, just for fun, think about some other cases where we have exponential expansion of many e-folds, or situations in other areas of physics where we have a similar phenomenon. One fun inflation is in biology. So we all came from a single cell. It expanded into the number of cells that we have today in our bodies. You can calculate how many e-folds that is. Make a guess. Yeah, that's about 30 e-folds. There is another situation which is actually very close to inflation. It's Another situation where we have something close to scale invariance, and which explains an important feature of nature. And that has to do with the fact that at energies higher than the mass of the proton, QCD is almost scale invariant. Right? So we have a theory that is almost scale invariant from, it could be all the way to the Planck scale. Let's just for the sake of the argument say it's all the way to, from the Planck scale to the mass of the proton. The theory is almost scale invariant. It's not exactly scale invariant. And when you get to the mass of the proton, the theory becomes very different from scale invariant. So it's somehow vaguely similar to inflation in the sense that during many, many decades in energy scale, we have almost scale invariance. And when we get to the scale of the mass of the proton, it ceases to be scale invariant. We have a drastic change in behavior. That's similar to, analogous to the end of inflation. Okay. Okay, so those are some other examples. We'll see that the second example is somehow quite closely connected, well, vaguely closely connected in terms of the symmetries and how the symmetries are realized. And finally, I wanted to mention another example from economics. So inflation, of course, the name inflation comes from the phenomenon of inflation, where money loses value and so on. And so I come from a country in Argentina where we had a lot of inflation. So since I was born till today, guess what the inflation was? What the total amount of inflation was? What? 7? 70? 7 to 8 e-folds. Yeah, so it was 34 e-folds, the factor of 10 to the 15. Yeah. Okay, so and the hyperinflation in Germany after the World War I was 10 to the 12. Anyway, so some fun numbers. So it's an exponent. Yeah, these exponential processes are common in nature. They're common in many fields, and yeah, they can easily generate very big numbers, right? And so here in the expansion of the universe, it's generating a very big universe. Yeah, it's surprising. Space is cheap, right? So we can create more and more space, similar to printing more money. It doesn't cost anything. It's curious, but that's how it seems to work. Okay, so now we'll start getting to. We'll start discussing quantum fields in Kerr space. So the first lecture was a kind of introduction, general introduction of inflation. I didn't derive all the formulas, so now we'll derive all the formulas. So from now on, hopefully everything will be clear, and I hope this will be a very logical derivation where there won't be anything unclear. And so if there is anything, very minor thing that is not clear, please let me know. Okay, so the first topic that we'll discuss now is quantum fields, quantum field theory in the zeta space. And we're going to look at the case purely of a massless field, so a massless scalar field, free scalar field in the zeta space. And so as I remind you, we consider the metric of the zeta space. We'll use conformal time, so it's convenient to use conformal time in this discussion. So that's the metric we will be working with. And I remind you that if we were to use the ordinary proper time, we will get something like this, where eta is equal to minus e to the minus t, right? So as we go to large times, eta goes to 0. And I'm going to be setting h to 1, so we'll restore h at the end of the formulas. So that's it. Okay, so that's the metric. That's the space in which we'll do physics. Okay. And what's the Lagrangian that we're going to consider? So we're going to consider the scalar field Lagrangian in this curve space, gradient phi squared. When we use those coordinates, we get d eta dx, 1 over eta squared, d eta phi squared minus dx phi squared. Okay. So that's our Lagrangian. So here, notice that there is only 2 factors of eta because we have the square root of g that has 4 factors. We have an inverse metric that gives the 2 factors. Okay. Now, we are going to use the symmetries. So one of the symmetries that we have is translation symmetries in X. So we can make X translations. And therefore, it's going to be convenient to Fourier transform the field. So we're going to define some fields phi k, e to the I kx, right? So this is just the usual Fourier transform. Okay? And this is in principle a function of eta, okay? So we just simply Fourier transform in X. So this is in the spatial coordinates. We haven't done anything in time. So once we do that, we get that our Lagrangian will be, there will be some integral, the 3k over 2 pi cubed. And then we'll have for each mode, so for each Fourier mode, we'll have a Lagrangian of the form, of the following form. So the eta phi k square minus k square phi k. Okay. So this is for each Fourier mode. Actually, because the field phi is real, there is a condition that phi complex conjugate is equal to phi minus k. Okay, so there is some kind of identification. So really, we could drop this factor of 2 and integrate only over half of the momenta. Okay. Now, here the important point is that for each Fourier mode, we simply have a harmonic oscillator Lagrangian. So this looks like a harmonic oscillator, right? This is like omega squared. But with a prefactor that depends on time. So this is essentially like a harmonic oscillator with a fixed frequency and a mass that depends on time. So the mass is becoming very large at late times, and it's very small at early times. Okay. Okay, so now we just simply have to solve this problem of a harmonic oscillator. The only unusual part is that the mass depends on time. How do we quantize the harmonic oscillator? Well, we could consider the equations of motion and then promote them to an operator equation. So this is the usual equation of motion. So this looks basically like the harmonic oscillator equation, except that there are these factors of eta square in between. Okay, so we solve these equations, and it's a simple exercise to show that the solutions are essentially like the usual solutions for a harmonic oscillator. So the usual solution would be just this e to the I k eta, right? But well, there is this other factor. So this is actually, one can check that this is a solution of this equation. Okay. So it's relatively simple. And we can have this solution, and we can also have its complex conjugate. So e to the minus I k eta 1 plus I k eta. Okay. Now the operator phi as an operator will obey this equation also. And so we can express the operator phi in this way. And there will be two operators here, one here and one here, that will be time independent, and I'm going to call them A dagger, and let's say B, so two different operators, right? This is just the name. We'll later, the name is suggestive, but for the moment, these are just simply two operators. They are two non-Hermitian operators, A and B. Okay. And remember, the field phi k is complex, so there is no relation between A and B, right? So very good. Now it will be convenient for us to put in here some numbers. So this is a normalization constant C. Maybe I should call it little so n like this. A normalization constant. This will be a number that for convenience we'll choose it later, so that A and B have. We'll later see that they have the canonical commutation relations of harmonic oscillators. That's something that we'll derive in a second, and we'll leave this normalization constant so that happens. Okay, so for a moment, this is just an expression for this operator. And so now we can determine the commutation relations of these operators by using the expression for the canonical momentum. So we have this Lagrangian here, over here, and so we can derive the expression for the canonical momentum. So we can derive by just taking the derivative of the Lagrangian with respect to phi dot, and that gives us a pi k. So this is dl d of d eta of phi, right? Phi k, and this is just simply, so there will be a 1 over 2 pi cube, 1 over eta square pi k, okay? Dot, so this is dot, or maybe prime, so it's the derivative with respect to eta, and it's the complex conjugate, okay? So this is the derivative with respect to phi k, gives us the complex conjugate of the time derivative. And here I use I remove the factor of 2 by integrating, let's say, only over half of the case, so that we are dealing with independent variables. Okay, so now we have that pi k, phi k, right? So this is supposed to be, right. So this is a delta function. Well, let me say k prime. So this is some delta function, k plus k prime. Pi cube. All right, so in position space, we have that, let's say, pi of x, phi of x, right? Okay, no, I guess well, I'm now confused about the 2 pi. But, okay, let's just derive this more precisely. So we have this Lagrangian, right? So for each Fourier mod k, this. So let's work just for each Fourier mode. And so this, for each Fourier mode, let's ignore the delta function. Well, let's say that this is I delta of k plus k prime. Okay. So we have that. We have this continuous integral. If we have a k different from the k prime, we'll get this delta function cubed. Okay. Is that clear, or should I say a bit more? Okay, so this is the canonical commutation relation that follows from that Lagrangian. And now we're going to simply insert the expressions for phi k and phi. So this was phi. So we have a similar expression for this phi prime. So we just simply have to compute here phi prime. So let me compute here phi prime k complex conjugate. So when we take the derivative, we'll get the factors. Okay, so we need to take the derivative of this with respect to eta. We'll get the factor of I, I k square eta, e to the I k eta. So we get, okay, maybe this, is this factor of I there or not? Let me see. No, there is no factor of I because there is a factor of I from here that cancels with this factor of I, so the leading term has no factor of I. Okay, is that clear? So there is this normalization constant n, and we have A, and we are doing the complex conjugate, so we have minus, and that's why we have this. And here we get the same thing, but B dagger eta e to the I k eta k square n. Okay. So we have these two things. We put them here, and what do we get? So there will be a term where we have a dagger, right? Times C, so the normalization constant squared over 2 pi cubed, 1 over eta squared, k square eta 1 minus I k eta. I mean, there are a few other terms like commutators between A and B, and those are even time dependent, so they give expressions which are not even constant, so those are set to 0. And then we are left with these commutators. This just simply follows from plugging all those things in. Delta k minus k prime. Yeah, this is, there is a minus I here because this is a pi with a phi. Would have been the opposite. We would have a plus I. Okay, so we have this, and so now we see that first of all, if we set the first commutator to 1 and the second to -1, yes, the mic is okay. Let me see. I don't know why it moves. Now, can you hear me now? Okay, now it's better. Let me see. Okay. Can you hear me? Yeah. Okay. I don't. Yeah. Well, I'll try to speak louder then. So this basically setting the normalization constant k cubed over 2 pi cubed equal to 1. Okay. So that's the value of our normalization constant, n, which is 2 pi to the 3/2 over 2 k cubed to the 1/2. Okay. Very good. So we've set the normalization. We'll see that this normalization is important for getting the right the right 2-point function. Okay, so now we have phi as an operator, and we concluded that the this A and A dagger obey the commutation relations that we expect for a harmonic oscillator, and the same for B. Okay. Okay. Very good. Now, yes, please.
So these operators, can they not depend on K?
Oh, yes, they do depend on K. Yes. Yeah, so to be more precise, okay. let me write a more precise equation. I should perhaps a of k, a dagger of k prime, is delta of k plus k prime, k minus k prime. Okay, so this is a more precise equation. Okay, so if we were to discretize k and put it on a finite volume, then it would be 1. If not, it's this. Yeah, so for each k mode, we have one harmonic oscillator. That's, yes. What? Yes. If k was, if we put the system in a finite box, so if we were to compactify x, then we would just get the Kronecker delta, right? If here we're doing the continuum expression, we get the delta cubed expression. Yeah, so this was, yeah, let me write just the correct formula, not the incorrect formula. so sorry for confusing you, sorry. We had a delta function of k plus k prime here. We had that in the right-hand side. So this is the equation that this derivation gives you. Sorry for being confusing. And thank you for the question, so that this should make sense. There shouldn't be anything vague. Okay, so far we wrote an expression for the operator. We derived that this is the expression. Okay, so here we haven't really done very much. But now there comes a very important point, which is what state should we pick, right? So if we're dealing with a harmonic oscillator, there is a special state which is the minimum energy state, okay? And that's the state which is annihilated by A's. So the vacuum has the special property for harmonic oscillator that is the minimum energy state. But well, here we have a time-dependent situation. Energy is not conserved, so we don't have a particular reason to pick this state. However, in this case, there is some principle that we can follow. So let's see. So let's consider what happens when eta goes to minus infinity. So that is the far past, right? So what are we talking about in that case? So we have the Sitter space. So there is x and eta, remember, goes like this. We are considering a mode with a given wavelength, right? So some mode with a given wavelength. And we are going into the very far past. So that mode, when you go to the very far past, has some wavelength that is well within the horizon radius. So it has a very small proper size, okay? So we're talking about a mode with, let's say, high momentum or very short wavelength in a sort of big space, which from the point of view of that mode at that time, it's expanding very slowly compared to the wavelength, okay? And so in that regime, we would expect that the physics should be essentially that of flat space. So it would be similar to flat space physics. And indeed, we see that in the solution. So if we look at this solution and we look at the regime where this mode has a wavelength much less than the horizon size, and that corresponds to times when k times eta is much bigger than 1, okay? Now, this wavelength is like 1 over k, and we're just taking an eta which is bigger than that wavelength, right? That's what this equation is saying. So this is eta over the wavelength of the mode, much bigger than 1. That's where this picture is valid, okay? When k eta is of order 1, that's the picture where these two length scales are the same, and then at very late times, that in this regime, that's much less than 1. I guess I should have written all of this with the same same scale. So because we are always talking about the same mode, right? So this is the point where the wavelength becomes equal to the horizon size and so on. Very good. And we see here that when k eta is much bigger than 1, I don't know, when this is much bigger than 1, we see we have the ordinary, essentially the ordinary harmonic oscillator expression. This term also dominates, so we have something with some prefactor that varies relatively slowly compared to the rapid variation of the exponent here, right? And that's this equation here is what we have in ordinary flat space. Okay. So we see from the solution that we have flat space physics, essentially. And therefore, it would be natural to think that this mode will be in the vacuum at that point, in what corresponds to the vacuum. Or we could select the state that would have, at least at these times, the lowest energy, which would be the vacuum. So the state that we are going to pick is a state that will obey this condition. So for all modes, so AK and BK are all annihilate the state. Okay. I guess I should have mentioned that because of that condition that we wrote over there, this condition here, the BK and AK are not independent, so the A dagger. So basically, this is like the A of the minus K. Okay. Okay, very good. So we have that condition, and so that has selected now the vacuum. So we choose this vacuum. This is sometimes called the adiabatic vacuum. So at the early times, the background is varying very slowly, so we can choose something that looks locally like the Minkowski vacuum, and that vacuum then, well, is chosen once and for all, because we are here, let's say, in the Heisenberg representation, where the operator depends on time, the state is time independent, and this is the state we'll have for all times, right? In the far past, we can call it the adiabatic vacuum. In the future is some state, right? The state in which the state we're considering for the fields. Okay, let me see if I'm forgetting to say something. Very good. So that's the conclusion. Now, let me see. Okay. So let me say exactly what. Let me emphasize a bit some of these pictures. So. So let me establish some nomenclature. So normally in the time regime where this mode is well within the horizon, we say that this mode is inside the horizon. At this point where k eta is of order 1, we say this mode crosses the horizon. And at later times when k eta is much less than 1, right? This mode will be outside the horizon. Notice we are talking about many e-folds, so this guy could be e to the minus 70, right? It's something very, very tiny. Now, when we take this picture, so in the final, I'm going here to preview how this will work in the future once we put in the end of inflation. So if inflation somehow ends here, and we join here the radiation-dominated FRW universe, then we'll have again that the size of the horizon will start increasing again. And this mode eventually will cross the horizon again, what we say is that it crosses the horizon and then it becomes smaller than the horizon size in the far future. So the time history of all these modes is that it starts well within the horizon, it's very, very small, then it crosses, becomes very large, much bigger than the size of horizon, and then eventually the horizon size starts growing again and crosses back. And here, what happens in this region depends on, well, late universe physics and what exactly this field is and so on. Very good. Now, for this case of the massless scalar, it's important that we said that when it was before it crosses the horizon, it's oscillating like a normal harmonic oscillator mode. Once it crosses the horizon, this mode really becomes constant. So notice that here, when k eta is much less than 1, we can neglect this term, so we can forget about this. And we can also forget about this phase, and this becomes time independent. Okay? So the mode is time independent once it crosses the horizon. And this is the case for a scalar field. So roughly speaking, if we were to plot those wave functions, so I'm going to make a plot of, let's say, the real part of this. Let's say it's 1 when k eta is very small, right? And then it has some variation and it starts oscillating with a bigger and bigger amplitude because this becomes bigger and bigger, okay? But it somehow, that's roughly the picture. So it oscillates, so that's when it's well within the horizon, crosses the horizon and becomes constant. So that's the time evolution of these modes. Now that's the case for a massless field. If we had a massive field, what would be the situation? This whole derivation would be essentially the same for a massive field. The difference would be that these functions would be slightly different. They would be Bessel functions. They would also oscillate in a similar way for early times, because for very early times, these wavelengths are very short, and the fact that the field is massive or massless, it doesn't really matter. So for very early times, they oscillate basically like these ones with e to the I k eta times a factor of k eta. But then at late times, sometimes sometimes these modes could go to 0, or they could have some other oscillations at later times that depend on the mass. That depends on whether the mass is bigger or smaller than h and so on, some factor times h. We'll probably discuss a bit more the massive fields later, but for the case of inflation that we'll care about, for the main fields like gravity and the scalar field, we can approximate them by massless fields. So that's what we'll consider for the moment. Okay, very good. Any questions? Let me see if I'm forgetting something. No. Okay, so now once we said all this, we can now calculate the two-point function in Fourier space. So here we are just going to compute the expectation value, and this is the expectation value in that vacuum we defined over there, right? So that special state that we are considering. And okay, so that's our final expression. So that's supposed to be correct with the factors of 2 and pi, etc. And what does this formula depend on? Well, it depended on the choice of vacuum that we chose. And remember, it depends also on this normalization constant, because when we insert this expression into this two-point function, what do? So we just simply insert two expressions like this at late times. So at late times, so that's the expression at late times, where k eta can be neglected, so this becomes 1. and this becomes 1, okay? So the answer is proportional to the normalization constant squared, okay? And then there will be, we'll pick the piece with an A here, with an A dagger here and an A here that gives a 1 or a delta function, right? And that's where this answer comes from. Is that clear? Yes? Okay. Again, normalization determined by the commutation relations, and then we had our choice of vacuum. Of course, you could also compute it at not at late time. So let me emphasize that this is when k eta is much less than 1, right? When it becomes time independent. So here, this answer is independent of the eta and eta prime of this. So in principle, here there is an eta and an eta prime, and so we're evaluating them at late times. Okay, so the 2-point function in the far future. Okay. So we could, that was the result when h was different from when h was 1. Now when h is different from 1, we can restore h by doing dimensional analysis and remembering that the dimension of the field is dimensions of energy. And so we get an h square here, okay? Or we could put the h everywhere in the in this, but it's not too convenient. Okay, so now we can go back to position space. So we could say, well, let's compute this now in position space, phi of x prime. We could ask, we could ask this question of what this answer is in position space. And when we do that, we will encounter an integral. So let me put, it will be translation invariant, so let me put 1 at 0. We will encounter the following integral, dk cubed over k cubed. So the k cubed comes from this k cubed, e to the ikx. And this integral is logarithmically divergent at k equal to 0, so it has an infrared divergence. And so this answer will be some kind of logarithm of, log of some long distance cutoff over x, okay? Okay, and that's it. So the scalar field in the sitter has this infrared divergence. It's a physical infrared divergence if we had a scalar field. So this vacuum is not, the state is not quite well defined. So we don't get well defined answers in position space. And exactly what we should do with this divergence depends on the context. If we really had a scalar field, massless scalar field in the sitter, we really have this infrared divergence, and well, that's too bad. No. So if we had a massive case, then we wouldn't have this divergence. Okay, so we could regulate the divergence. We could add a little mass to the field, or, well, depending on the precise physical situation, we will deal with this divergence in different ways. So in the problem we are interested in, this divergence will not be physical. So when we go back to gravity waves or scalar fluctuations, it will not be relevant because we are only going to be considering differences of fields. So the difference in the value of the field here on Earth versus at different points in the sky, and in these differences, these divergences will cancel. So we don't have to care about those divergences for those cases. Okay. Very good. So now let me see. The wave function. So here we just computed the expectation value, but let's talk about the wave function for. Let's talk about the wave function So what we have is a harmonic oscillator, and the wave function of a harmonic oscillator is Gaussian, okay? And so we can determine this Gaussian from the 2-point function. So just from the 2-point function, we can see what the Gaussian is, at least at late times. And so we find that the wave functional, let's say as a function of phi, for each Fourier mode, goes like something like e to the minus k cubed, right? Over h squared phi k. Or the full wave functional would contain some integral d3k over 2 pi cubed. Okay, so that's the wave functional, the full wave functional for the field. Now, normally when we do quantum field theory, we don't talk too much about the wave functional. We mainly think about expectation values or particles and so on. In this case, it's useful to think about the wave functional also. It's what the wave functional for the fluctuations, because when we are looking at the primordial fluctuations, we are basically taking a snapshot of this wave functional. We are just sampling this wave functional, and we get a particular profile from this probability distribution. Okay, and what we actually are measuring is this particular profile. Okay. Now, let me. So we have k eta, right? Now, this is the wave functional when k eta is much less than 1, right? So what the wave function for the field looks like. So if we thought about the Schrödinger picture wave functional as a function of k eta, right? So initially we have a field with very tiny mass, right? So we would expect that wave functional to be very broad, right? So some kind of broad wave functional. So this is psi, roughly a picture of psi. As k eta becomes smaller, we could have a narrower wave functional. And finally, for very late times, we naively would expect that the wave functional of a field with very tiny mass should be a very tiny little Gaussian. This would be like the wave function for a field with a given mass. So let's say we had a harmonic oscillator and we make the mass smaller and smaller and smaller, we would find a narrower and narrower wave function, okay? But that's not the problem we have here. The problem we have here is something with a time-dependent mass, okay? And what happens is that when k eta is large, this mass is varying relatively slowly compared to the frequency, and the wave functional sort of tracks what you would expect for a field, for a harmonic oscillator with constant mass, right? So the wave function becomes thinner. But once you cross this k eta equal to 1, the wave functional stays of this size, right? So the actual correct wave function here is not this one, but is basically similar to the one we had for k eta equal to 1. So it becomes time independent. It does not get narrower and narrower, as you naively might have expected if you were tracking the wave function of a field with a constant mass, but smaller and smaller mass. It becomes constant and, in some sense, much bigger than you would naively expect. Okay. Yeah. Well, we know from doing the computation that the wave functional is independent of time after when k eta crosses 1. Right? We know it from this expression. So if we calculated the 2-point function, we would get for general eta, we would get roughly the modulus square of this, right? And which has some dependence. But when k eta becomes small, it just becomes a constant. Okay. Is that clearer now? Yeah, so normally people sometimes say that the wave functional at the end has a very high occupation number. So if you wanted to express this wave function in terms of the wave functions of a harmonic oscillator with very tiny mass, it would have very high occupation number because it's very broad. Okay. But well, I think thinking in terms of those occupation numbers is not the right, perhaps, way to think about it. It's perhaps better just to say, well, we have this wave function, I'll say explicitly what it is, and you know, it's a very, very clear and picture. Okay. Now, people sometimes also there is the question of there is the following question. So initially we have some kind of quantum harmonic oscillator, right? We have some quantum fields at very short distances. And eventually we have this field that is defined over macroscopic scales, many, many horizon sizes, that looks basically like a classical field. In fact, you know, the distribution of galaxies and so on is classical. So when did this transition between quantum and classical happen, right? And is there something mysterious about this transition or not? Now, for that, it's useful to go back to this computation that we did of the commutation relations between phi and phi dot, right? So a classical field is something that, let me remember that pi was equal to phi prime divided 1 over eta squared, right? And we had that pi and phi had canonical commutation relations, let's say, of order 1. I'm ignoring delta functions. And so that means that, so let me write this as 1 over eta cubed times the derivative with respect to proper time, okay? So this was the derivative with respect to eta. This is now the derivative with respect to proper time. Now, this implies that the commutation relation between the proper time derivative of phi and phi itself now goes like eta cubed, okay? So I simply put this equation in here and put the 1 over eta cubed that we have here, we put it on the right-hand side. And what this is saying is that when we essentially cross the horizon, if we average the field over, let's say, horizon size, and we look at its value and its proper time derivative, they start commuting with each other, okay? Now, the later universe, when we look at the evolution in the later universe will care about phi and the proper time derivative of phi. It will not care about the canonical momentum. So it will mainly depend on these quantities. That's what we will be measuring. And in fact, the proper time derivative of phi will be essentially 0. Those are the initial conditions for the later universe evolution. And so these variables, we can more or less very directly see that they become classical in the sense that they become commuting with each other. And this will be the variables that we will care about for the later evolution of the universe. Okay. Yeah, so maybe one more philosophical point conceptual point, before we continue with more technical discussion. So we've chosen this particular vacuum. We said we had a wavelength mode which is size smaller than the horizon size, but in order to talk about this mode, it has to be a wavelength which is bigger than the Planck. The proper wavelength at this time has to be bigger than the Planck scale, right? If it's smaller than the Planck scale, it's not really part of our effective field theory. But we have a very large number of phi-folds, so it's easy for this mode to become shorter than the Planck scale, okay? And so this, the effective field theory in this expanding universe is something peculiar, where modes are, that there are modes that are at later times in the evolution are part of the effective field theory, but that earlier parts in the evolution are not part of the effective field theory because they have very tiny wavelengths. Now, the idea is that these modes, when they become part of the effective field theory, they come in the vacuum, in something that is locally looks like the vacuum, at least at short distances. And then these modes come in the vacuum, and then in some sense, you could say they get excited when they cross the horizon, actually in this. That's one thing you could say. But this fact that they come in the vacuum is an important, let's say, if you wish, it's an assumption or it's some prescription that is consistent, and we'll later see more how to use it in practice, how you impose in practice this condition that the modes come in the vacuum. It amounts to a certain, when you do Feynman rules in de Sitter and so on, or perturbation theory in de Sitter, it amounts to a certain I epsilon prescription, a certain prescription for how to deal with the integrals when you go to very early times, okay? But that's a conceptually important point, and in some sense, it's a prescription that we have for dealing with the space-times. You could say, well, I don't like it, maybe when this mode, then maybe something new that happens when this mode, when the proper wavelength, lambda proper, becomes L-Planck, maybe the mode does not come in the vacuum. Maybe it comes in excited. I can make the theory where it comes in excited. And then that will lead to a slightly different prediction. Okay. But there is not, we don't have a complete theory of quantum gravity and so on, so we cannot say that that assumption is wrong. It's just, we make the assumption that the modes come in the vacuum. That's what we do. So that's the conventional assumption. You could explore people have explored the alternative ideas, okay, where it does not come in the vacuum. So that will give you some correction. Very good. Well, maybe I'll make one more point. Is that if you make this assumption that modes come in the vacuum, then there is basically a unique choice of vacuum that depends only on your Lagrangian. So you choose a Lagrangian with this, just only choosing the Lagrangian, you get some vacuum that comes from this condition. And this condition can be imposed both for free and interacting fields. So it's a prescription you can extend to all orders in perturbation theory. If you said that the modes do not come in the vacuum, then at higher orders in perturbation theory, you'll have some issue. Well, you could, again, choose a different vacuum at each order in perturbation theory. So it's a slightly less well-defined procedure. It might be the right procedure. We don't have the full theory of quantum gravity. But normally when people do computations, they assume this assumption of starting with the adiabatic vacuum that I mentioned. But it's certainly not unreasonable to consider a different one. So, yeah. Well, they're hard to. Yes, if your choice is too wild, yes, there are some constraints. I mean, they could lead to very large non-Gaussianities and so on. If you choose your choice is very wild. If at the level of the two-point function, it's hard to see because they will lead to, so it will be like adding extra particles. And as far as I'm aware, there is no, well, I don't know. I don't really know. But yeah, I think, well, I'm tempted now to say something that I was planning to say later, that with non-Gaussianity, this is a very clear way to test this, to see this. Let me just give you a quick answer. So if you look at the three-point function and you look in the configuration of a collapsed triangle, then this vacuum gives you no singularity in this regime, but a different vacuum will give you a singularity. So this would be an in-principle test of this idea. Of course, non-Gaussianities have not been seen, so it's Okay, so any other question?
Sorry,
Yeah.
very naive question. The fact that in a different vacuum choice we have a singularity in the spectrum.
Yeah.
It means that the right choice is the other vacuum, or maybe there is an issue with the computation of the spectrum.
Well, the computation of the bispectrum will depend on the choice of vacuum, right? And you get different predictions for the two choices. And then you could go and see in nature what you get. Yeah. So yeah. So we don't see any bispectrum, so we don't see whether it's singular or not. It could be that there is a very tiny little singularity that we don't see, or yeah. So we cannot conclude anything at this point, other than we didn't have a highly excited particles. I would have seen this contribution to the bispectrum. Yeah. But yeah, so part of the problem is that experimentally we have only access to the 2-point function. We are only measuring the 2-point function and over a finite number of modes. So we are not even measuring that with with infinite precision, let's say. Or, yes, as a theorist, you would like to be able to measure, all endpoint functions and so on. And if you could measure all of this, then we could answer these questions. But with the partial information that we have, there are many possibilities that are still consistent with the information we have. Yeah. Even this question, so I mentioned the experimental result, for example, for the running of the spectral index, right? That is based on the assumption, so you put as a prior that we have some distribution with a constant power, with some power law, right? And then you determine the power of K. I mean, the running of the spectral index is whether here there is some extra power. If you assume that, then you can fix that extra power, is what I discussed at the beginning of the lecture. But you could also come and say, well, no, I have two separate powers. I have one power for some range of k's, and then there's a break, and at some other point there is a different power. And that also fits the data. But there are extra parameters, the place at which it breaks, and so on. So we should... I want to emphasize that we really have partial information. We should not think that we have completely seen this power very, very cleanly, as cleanly as we have it theoretically.
We play with the data just next to the CMB scales, and then we are free to make whatever we want.
Yes, but even at the CMB scales, it's not that we measured very precisely the power spectrum at each CMB scale, and then we seen that we can only have a running power. We see some data, and then we fit a running power, and we get that deviation. But we could also have fitted different types of powers if we allow for breaks, for example. I'm not sure if I'm being clear.
No.
Yeah. Yeah. Okay. And something somewhat, well, a problem which happens here is that if we're looking at the scales, sort of big scales, like the scales that the CMB is probing and so on, we have this phenomenon of cosmic variance, right? So we would like to determine we have a theoretical prediction for the 2-point function. Well, I erased it. But in reality, we just measure this 2-point function for only our universe, okay? So, for example, for the highest modes in the sky, let's say the angular momentum, let's say 2 modes in the CMB, there are, let's say, 5 angular momentum modes, and we just measure those 5 modes. And from those 5 modes, we'll try to see whether it matches or not with the Gaussian that we expect, right? So we predict the Gaussian, and we measure 5 points. And from that, we need to find whether it's a Gaussian, and whether you cannot find that. So you cannot possibly, from 5 points, determine whether it's a Gaussian and exactly what the width is. I mean, you can determine with some error what the width might be, or this phenomenon is called cosmic variance, that we have only one universe. And as we go to higher and higher angular momentum modes, then we have more and more, and we get tighter constraints, but we always have this issue. It will just be a smaller issue. Okay. But yeah, it's a curiosity. You might wonder whether the fundamental theory really makes a definite prediction, or maybe it uses this randomness in an interesting way. Okay, so so far we've talked. I should. Do I have 15 minutes or?
Oh, yeah, but
Whatever. Yeah.
we had a flexible, of course.
Oh, okay. Well, let me see. I was going to now start talking about the more realistic computation. Let me see. Or we could end here, or I could go 15 more minutes. Yeah, what do you prefer? You're not too exhausted? Okay. So now we'll go to the inflationary computation, and we'll discuss. So far we treated the scalar field. This is not exactly the computation we want to do. So let's talk about the computation we actually want to do. So now we actually go to the inflationary computation. Now, before I continue, another philosophical point. I think this inflationary computation of the fluctuations is something really cool. It's like the most interesting application of quantum mechanics. I think it should be taught in undergraduate quantum mechanics. It's just a harmonic oscillator with a time-dependent mass. So it's not something outrageously complicated. It's something that I think should be taught in undergraduate quantum mechanics. Yeah, quantum effects giving you the structure of the universe. What could be cooler than that? It's just, but well, so now so now we'll go into some more details. So, but they are not outrageously complicated. They are some. So what do we have? So we have a metric, Jij, and we have or G mu nu. And we have a scalar field, okay? Now, the philosophy is simply that we start with a uniform background. So we start with a background, which is just the expanding universe where all fields are uniform, but it's the inflationary solution. So we have some background, which is it has some scale factor as a function of eta, and the usual metric, and a phi, which is a function of t, right? And then we're going to expand the metric and the scalar around these background solutions. So we'll have some, let's say, delta G mu nu, which is an expansion, and delta phi. These are independent of x. They're independent of x. This will depend on x and time. Okay, that's the idea. Now, as before, as in the case that we had for the scalar fields, we can use translation invariance, and so all the fields will be expanded in Fourier modes, and also we'll use SO3 invariance. So then it's convenient the delta G mu nu to, so there is delta G00, there is delta G0I, there is delta Gij, right? So the various components of the metric. And this can be then further decomposed into various modes. I forgot to mention one thing. So we're going to take the Lagrangian and we're going to expand in quadratic order in the small fluctuations, right? So we have the uniform background, and so the linear order just will vanish because the background obeys the equations of motion, and then we expand to quadratic order. So everything will be the Lagrangian to quadratic order, the equations of motion are linear, and we Okay, so this will give rise to something. So we're going to decompose the modes according to their SO3 transformations. So this will lead to something we could call a scalar mode. So it's some function, so it's e to the I kx times some function of time. This gives rise to two types of modes. One will be a scalar and one will be a vector. So the scalar is the piece that is proportional to ki times some function e to the I kx and then some function of time, so some function of time. And then there will be another piece which will involve a vector part, e to the I kx. So this is some polarization vector that is orthogonal to k, right? Yeah, more precisely, I guess what we are doing is we are taking this SO3, and there is one vector which is k, and then we are looking at the SO2 around that vector. We're decomposing the modes in these SO2 quantum numbers. That's a more precise thing of what we are doing. So this thing that had three indices could be along the k direction or perpendicular to the k direction, in which case we have two possibilities. So there are two possible values for v, okay? And for this guy, we similarly have a piece that is proportional to delta ij, a piece that is proportional to ki kj, and then there will be some piece that is proportional to ki vi. And then a piece that is completely transverse. So let me call it epsilon ij, where this epsilon is traceless, so epsilon ii is 0, and k times epsilon is 0. Okay. So these are the possible, somehow, by some abuse of notation, we could call, yeah, let's say helicities. So we pick the vector k, and then the SO2 transformations. So we have two scalars and vector and two vectors and another scalar here. Okay. Okay, very good. So those are all the modes that we have. We also have a delta phi, which is another scalar. Okay, so we have all these modes. So this seems to be more than we expected, right? We expected one. This guy here we did expect, right? The gravity, the transverse, the graviton fluctuations, and we also expected some kind of scalar, but we seem to have all these extra modes. And of course, what gets rid of the extra modes is the gauge symmetry. So we also have gauge symmetry, and again, so the gauge symmetries can be similarly expanded. So we have a time gauge transformation. Well, maybe I was calling it eta. Eta goes to eta plus some epsilon sub eta of the other variables. So this looks like a scalar in the sense that it doesn't have any indices. And then we also have the delta xi, which are some epsilon i's, and this again can be decomposed in a piece that is proportional to k, and some piece, let's say v tilde I, which is orthogonal to k. Okay, so we have basically two scalar transformations and one vector type transformation, or two, because there are two possible choices of v. And this basically, those get rid of the extra modes. The counting is the following. So by doing these transformations, we can somehow remove some of these degrees of freedom. So let's say, for example, we are talking about the scalars. So there are two scalar gauge transformations, which we can use to remove some of this this degrees of freedom, we can remove 2 of the scalars. So for example, we could remove these 2, set them to 0, set the fluctuations to 0. That would be a choice of gauge. But then we are still left with 2 other scalar, well, 3 other scalar degrees of freedom, this one, and that one, right? And the idea is that so in these gauge systems, we usually also have, well, we have constraints, right? And for each gauge transformation, we also will have one constraint, and this constraint will get rid of one of the degrees of freedom. Okay, so for each gauge transformation, we also have one constraint. So we remove 2 degrees of freedom by the gauge constraint, by the gauge choice, sorry, and then the constraints that are part of the Einstein equations, which are not dynamical, but they are not second order, they're either first order or 0th order. They will remove 2 other degrees of freedom, and we are going to be left with just one scalar, which is what we wanted. Okay. And I guess I'll finish here, and then I'll discuss a bit more we'll discuss this a bit more later. Which gauge choices are appropriate and how to do the full calculation. Okay, thank you.